introduction. Can you hear me and see my slides?
Yes, we can.
Okay, thank you. So today I'm going to present our recent work, which called HatRPC, which means Hint Accelerated Apache Thrift RPC over RDMA. So this is the outline. Okay, let me move it. Okay, so this outline talk, first of all, I'll give some brief introduction of the background of this work and why we are going to do this work. And then we'll discuss the design and then some of the evaluation studies and then conclude the talk. So nowadays, I think probably we already know that in many data centers or HPC centers, both the hardware and software are developing towards multiple different ways. For instance, you put a lot of different heterogeneous components, and then your applications also becomes heterogeneous as well, right? So just like showing this figure, if you think from database perspective, you probably have different database servers running in different nodes, and then you have different clients query on different database servers. And then among these database servers, as well as the clients to database servers, you have different operations or different communication behaviors, right? So some of them like heartbeats, some of them data shuffling, some of them like scan updates or batched updates or get query, something like that. So if you look into these scenarios, you can see that many of these operations actually have different kind of requirements in terms of communication characteristics, patterns, resource requirements, performance goals, something like that. So this situation actually will be even worse with the emergence of cloud computing, where multiple applications running simultaneously in one cluster or even on one node, right? So heterogeneous applications typically, require different ways to design their underlying communication or I/O runtimes to get the best performance. But now the challenge is that how to individually and efficiently tune applications in this scenario. This is a big concern. So as we all know in this community, right, RDMA has become one of the most promising communication protocol in the next generation data center infrastructure. So this is a networking technology that enables access to remote machines memory without much involvement of CPU. So RDMA provides low latency and excellent bandwidth, and is widely used in HPC field. Now it's also moving to data centers, cloud computing, deep learning, big data, everywhere. So now, however, if you look at the how RDMA, how we program is RDMA, probably in this community, right? All of us or most of us are experts, so you may not feel it's hard. But if you stand in from the undergrad students or even graduate students level, right? When they start learning RDMA, when they start using it, when they compare with sockets, they definitely will feel, okay, it's not easy, right? For instance, let me just give some examples here. If you think a simple hello world program, if you wrote it with like native verbs, so for instance, there's a lot of examples on the internet, right? I just choose some of them here. I just pick one of them actually. This is based on RDMA CM, which is relatively simpler already. So it's also around 600 lines of code. So but I think I got some comments that how about the UCX and the libfabric? So for UCX, I think there is an official hello world from the repo. As you can see, if you open this link, you can see that there's around they need around 745 lines of code to write a professional hello world. Okay, I agree that this hello world is pretty comprehensive and professional. So, but even for a naive hello world with UCX, I guess maybe still 500 lines of code is needed, I believe. And then for libfabric-based hello world, I couldn't find a official example. So, but I can find a ping-pong test. So this is like 2,335. Of course, this is not apple-to-apple comparison, but you can imagine that if you half it, right? So it's like a simple hello world maybe. So then it's also around 1,000 lines of code. So even though this, with the help of UCX and libfabric, the programming becomes simpler based on my experience, of course, but still, you still need spend around hundreds of lines of code to write a simple hello world example. Now, what's the real problem, right? Hello world is just a simple case, but in practice, right, in order to get good performance and efficient designs for those heterogeneous application scenarios, like I mentioned in the previous slides, we are not just design one RDMA schemes or communication schemes in our runtime, right? We typically have to design many different kinds of RDMA communication schemes in our runtime to get better performance for different kinds of application scenarios. Let me quickly survey some state-of-the-art design on RDMA schemes in the literature. Okay, so that you can see how many of them actually are available. Actually, this is just a small portion of it. If you look into more papers, you will see a lot of more different kind of designs available. So like I said, there are several previous work that propose new RDMA communication schemes for different kind of scenarios. Like, let's start with a simple one, like eager send receive, right? This has been utilized many years in many HPC runtimes such as MPI or others. So eager send receive use RDMA messaging and involve CPU to do a copy for receiving a message. And then you can also do direct write send, which means you use an RDMA write and plus send to notify the arrival of the messages. And then you can also do some optimization, like you can do chain write send, which means you put RDMA write and RDMA send requests in one post send operation, so that you can chain them together, save some time. And then, of course, you can also use direct write immediate operation, so that you can directly write to remote user buffer and then notify remote CPU of the incoming message. Of course, you can also design like RDMA read-based rendezvous and write-based rendezvous to make appointments with the receiver, so that the receiver can reserve buffers for senders one-sided operations. This will free memory to be statically pinned down for peers. And then there are some other designs from many cloud computing or data center environments, so that they call like a PLAB, FARM, RFP. All these schemes actually trying to leverage RDMA read-based protocol to offload workload from the server to the clients for better scalability, so that server can be bypassed in a large portion in the business logic. So, however, given such a large pool of, this is just the like I said, I mean, small number of schemes we listed over here. But if you do more survey, you can see the large pool of available RDMA schemes in many designs. There's still no among all of the things, you can see there's still no one size fits all solution for heterogeneous HPC and the data center application scenarios and the environments. This situation will bring significant challenges for the RDMA community to achieve both high performance and high productivity in different kind of application scenarios. So with a large pool of our available RDMA schemes, we need to investigate their performance in different kind of application scenarios, right? So therefore, we conduct some experiments to re-examine their performance in RPC systems using a micro benchmark. So here, because we are trying to, first of all, we are trying to learn the latency. So we typically, for achieving good latency, we use busy pooling. So when busy pooling is used for small messages, the rendezvous schemes have higher latency than schemes using eager send receive or direct one-sided operations. This is actually, we already learned these things when we do MPI designs, right? For example, rendezvous is like 140% slower than eager protocol and in the left figure, but it can be 54% faster in the right figure. Among the direct write schemes, direct writing with immediate has the best performance, achieving up to like 13% or 22% improvement over direct write send and chain write send, respectively. So moreover, schemes designed for specific application don't show superior performance in RPC systems. RP is better than PLAB and the FARM scheme, but up to 47.2% slower than direct write with immediate. But then if you look at the throughput, the story may be a little bit different, because for Supercritical protocol, typically, we prefer to use event-based or something like similar to that based pooling approach. So hence here we show the performance results when event pooling is used. For small message size like 512 bytes, like a direct write with immediate still has good performance beating other schemes. And then in addition, if you look at the RPC design, which is a RDMA read-based server bypass design, it doesn't improve performance over simple schemes. when the message size is small. But for large message size, like 128 kilobytes, RP's hybrid schemes actually yields better performance than direct write with immediate a little bit. And the RP with event pooling is actually very suitable and for full and over subscription for large payloads. So with this, what we observe is that through this empirical and the preliminary experiments, we actually find two problems. First of all, RDMA performance is high, but its productivity is relatively low. Because of this, we are thinking that can we design an approach to reduce this productivity issue, especially whether we can automatically generate some efficient RDMA-based communication substrates for data center applications. And the second thing is, since the results show that there's no one-fits-all solution available for heterogeneous applications, then how can we propose an approach that it can satisfy different communication requirements on various RDMA schemes in data center applications? In the meantime, it can also guarantee that the effectiveness and efficiency of the generated RDMA-based schemes for different applications. So with this, I can quickly go over with our designs and see what's the basic idea behind it, and then what kind of implementation issues and how to use it. So the key ideas of HatRPC is that, because like I said earlier, we observe two problems. One is RDMA productivity, the other one is no one-size-fits-all solutions. So we propose two different key ideas for these two problems individually. One is that we are going to use RDMA-enabled RPC frameworks so that RPC is relatively simpler than RDMA-directed programming, right? So here we choose to use Thrift as an example. Later, I will explain why Thrift is a good example for that. And then for the second problem, we are trying to say that, okay, look, even though there's no one-size-fits-all solution, but probably we could allow users to identify their communication requirements through some kind of high-level semantics like hints, and then we can put these hints into the interface description language-based RPC description files, right? Like IDO files, and then we can use these two ideas and then generate combine these two solutions or two ideas. We can generate the final RDMA-based communication runtime so that it can be linked into the application, and then they will get benefit automatically. So like I said, why we choose Apache Thrift, because this is a very well-known RPC framework from the Apache GitHub, right? So it's like gRPC and the other RPCs. Thrift RPC provides different language support. You can write your application with C, C++, Java, Python, whatever. They support a lot of different kind of languages, and then it also running on different kind of operating systems. And then internally, they also have a different kind of transport support. So like you can use memory buffer, pipe, TCP/IP, and the domain socket, something like that. And then for our work, we contributed RDMA, especially for the hint-based RDMA communication runtime into this architecture. So this is our proposed design. Based on Thrift IDO abstract syntax, we insert hints in functions and services definitions as shown in the left figure. We define hints as a set of key value pairs and organize them in a hierarchical manner. So as shown in the right figure, there are surface level hints and function level hints. And then surface level hints can be applied to all functions in an RPC service, while a specific function level hint can override the particular setting. And so in this way, we can make heterogeneous application flexible to customize the behavior and optimize the performance. Moreover, we also define hints for client side and server side. So in this way, you can define your needs in much better or much better granularities. And then this is also because the communication pattern or requirements may be also different from the client side and server side perspective. So then this is how the flow of how the code can be automatically generated with our extension to the Apache Thrift compiler. So code generation, is not laborious work compared with original Thrift. So we define new rules for Flex to generate the lexical analyzer and the Python to generate the pattern. So you calling our HatRPC code generator will output the hints as a map with the desired surface and step code. And our code generator will also check the validity of the hints setting and optimize the layout of the map by merging related hints and discarding duplications. Hence, a preferred application using original Thrift can be augmented with hints without source code modifications. So let me give you one example. If you, I'll give one example after this. After we introduce the HatRPC full architecture. So the right figure here shows that the system architecture of the HatRPC and show how the hints are passed and processed. As you can see, that actually we can enable hint to be defined by the in IDO level, and then we keep maintaining and managing these hints, and then transfer them across layers until it reach to the RDMA low level RDMA communication layer. So the underlying RDMA engine has implemented several RDMA schemes, pooling mechanisms, and memory management strategies. And the hint translator is responsible for hint processing and selection. To isolate mixed TCP and RDMA collections, we introduced the TRDMA layer as the counterpart of T-socket in the original Apache Thrift. TRDMA passes the hints to the RDMA engine and handles the RDMA collection establishment. So because of time, I cannot go over all of the details, but you can imagine how this one was transferred from the application code until to the end of the RDMA schemes being implemented over verbs. So now let's take a look example how we can use like HatRPC to design echo service, right? So first of all, step one, you can just write a high-level HatRPC IDO files. You can define what's your interface, and then what's your performance goals, concurrency possibly, and then the payload size possibly from both client side and server side. But of course, there's other hints. You can look at our paper and get more details. And then you can use our HatRPC generator to just combine this IDO file, and then it will automatically generate the stops from both client side and server side. And then step three, of course, you need to implement your server side handler logic, right? Because this is echo service, so it's very simple. We just return the payload back to the client. So then this is the server example and the client example. So I don't want to go over details, but the most important thing is you can look here. The code is exactly same, almost exactly same to the socket-based code. The only difference is that instead of T-sockets, you can change to TRDMA. That's all. So this is the echo surface, but if you use our approach to implement RDMA enabled hello world example, it only needs like 70 lines of code, including headers and everything. So this is a simple example for echo surface and hello world. But if you look at the how we are able to apply HatRPC into a real NoSQL database, so we designed a prototype called HatKV. So this is actually a simple key value store on top of HatRPC, and then HatKV uses the RPC service to communicate the data across between the client and the server, and then the server side backend we use RMDB as the storage backend, and we show an example of how if you use YSSB to test or to run on top of our HatKV design in the right side figure. So here we extend or optimize the YSSB with hints, and then we add multi-get and the multi-put operations into YSSB and mark them as throughput critical or throughput centric functions, while put get to be the latency centric functions to mimic the different application scenarios in the real data center environments. And the other hints like concurrency and the payload size are set accordingly as well. Moreover, hints are exploited to tune the configuration of RMDB because, like I said, we maintain these hints from the application side until to the backend engine, right? So this hint actually can also be used to tune your backend storage system as well. So now let's take a look at the evaluation and see what kind of performance benefits we can achieve through our design. So of course, we have to in our work we evaluated with Mellog's Collex 5 IBEDR, but of course we can apply to other like HDR maybe with the newer version of InfiniBand. And then this is but of course this can be, I believe this can be easily ported to other RDMA networks like Rocky or something like that. So let's take a look at a latency benchmark performance. So here we compared with HatRPC with hybrid eager renew. Hybrid eager renew is like what we have been doing this many years in MPI runtime. Right? Small message we use eager, and then large message we renew protocol. And then we also implemented the redirect write send and the direct write with immediate and RFP. So all of these protocols are state-of-the-art communication protocols in different or schemes on different research works or MPI libraries or something else. So all of them have very good performance. Okay, so just like we showed over here, their performance actually very close. But of course, some of them may not be designed for latency scenario, just like RP is not performing well for large messages. Otherwise, all of them actually achieve very good performance. But if you look at our HatRPC design, we see that HatRPC can automatically select the best schemes over during different kind of message sizes, and then we are able to achieve the best performance compared with other protocols. And then in terms of throughput, we set the performance goals to be throughput centric and run other schemes with even pooling as well. So HatRPC can automatically switch from the direct write immediate to RFP when the system is over subscribed, because earlier we learned that RFP actually is doing well for the over subscription case, and also it's actually good for large message. The results show that for throughput perspective, okay, the results show that HatRPC can improve the performance by up to 20% for 512 bytes message, and then for 128 kilobytes message, HatRPC can improve by up to 56% compared with the other solutions. And then, like I said, we designed the HatKV, co-designed a NoSQL store with HatRPC called HatKV. And then to evaluate HatRPC's applicability and efficiency with other applications, we test HatKV with our extended OSSD workloads. And then here, we also choose to compare with like ARGRPC and then HERD, PLOF, and RP. Or like I said, all of these things actually used in other key value store environments as well. So they're also designed very well. And then HatRPC, as we can see here, HatRPC function level settings can set the function level of hints for each RPC course as shown before. And then for the write-heavy workload A, HatRPC service improves latency by up to 73%, and HatRPC function can improve up to 80%. However, since HatRPC service ignores different RPC cores characteristics and needs, it can be slower than PLOF and RFP, while HatRPC function always yields best performance. Here, because if you blindly set the hints, sometimes it may also have some side effect on some of your operations. That's also understandable. So, and then if you look at the other case, so here HatRPC service and the HatRPC function can gain a speed up to 2.7 times and 3.8 times over other RDMA schemes respectively. And then for the read heavy workload B versus B, so HatRPC service and function can improve the latency by up to 84% and 85% respectively, which is pretty good. And in terms of throughput, HatRPC service and HatRPC function can also gain a good speed up compared with other schemes. So with this, let me conclude talk so that I can give some time for the discussion and the questions. So in this work, we re-examined the existing RDMA schemes and their performance in RPC system, particularly in RPC communication protocols or communication schemes. We propose a prototype called HatRPC. Of course, this is I believe that's the initial step. We are trying to explore whether it's possible to bridge the gap between how to satisfy different kinds of application needs, and also how to reduce or significantly reduce the programming overhead or programming time with low-level RDMA primitives. And then we use this approach to bridge these two gaps together. And then we bring a concept called hint accelerated RPC framework over RDMA. And then we specially designed and implemented into the Apache Thrift runtime and stack. So we see that through leveraging hints, we can significantly improve the performance in different scenarios, and we can also significantly reduce the programming overhead or significantly improve the productivity when you use RDMA-based programming to achieve this kind of benefits. And then to show the this is like an effective, if it is an effective and efficient solution, we actually co-designed the HatRPC-based key value store, HatKV, with AMDB as the backend, and we also extend the YSSB to to mimic different kind of application scenarios in the real data center environments. So as you can see that we can really achieve up to 85% improvement over the other state-of-the-art RDMA schemes. Of course, this work was done by my student Tianxi Li and Haiyang Shi. So, and also this was in part supported by NSF grant. So thanks to all of them. And if you have an interest to our work, and please feel free to download our SE 2021 paper. And then there are a lot of details about how this was designed and implemented. With this, let me thank for your attention, and I'm happy to take any questions.
Cool. Thank you very much. We have one question queued up so far.
Okay.
Is the choice of best algorithms based on hint systems specific, or is it generic?
It's actually this is a very good question. Okay, so it's actually the solution is generic, but in the meantime, you also need to maybe go back to this slice. Your runtime needs to be sorry, let me go on. Yeah, so your runtime needs to design in has a lot of different kind of RDMA schemes available in your runtime, so that hints can be used to tune and learn which protocol or which runtime or which schemes is the best suitable case or suitable designs for the particular function call or service, RPC service, right? So it means that you have to use these schemes to tune your system a little bit, but once this was done, and then for the future RPC call or RPC invocations, they can automatically choose what's the best RDMA schemes available in your runtime, and then automatically get the best performance to your application.
So the follow-up question: is there a training phase?
Yes, but currently kind of a training phase, but we did it in advance with our benchmarks.
Okay. One asks, could one add Java bindings to this, as a number of big data users would find it easier to integrate this into their current workflow?
I think so. I mean, because our right, many big data systems actually is already using Apache Thrift, right, or is already using these Thrift-based IDO systems, right? So to our designs, we just extend the IDO with optional hints. Okay, so in the worst case, you don't need to even put any hints. Okay, we still work. The only thing is that we cannot, take advantage of some of your requirements and then translate it into our low-level designs, optimize our low-level designs. But remember that, okay, if you even do nothing in your IDO files, you can still get the benefit from our RDMA designs. Okay, sure. Internally, we also have a lot of automatic adaptations available. So, but with your hints, I just want to say that we can do better choices. Okay. So that's the key message or key takeaways.
Fair enough. Nice work.
Thank you.
Well, if there's any other questions? Okay, we'll be taking a 30-minute break, coming back at 10 o'clock a.m. Pacific, where we will have